let me try this. So let me just start again, start over. So the first thing is we get somebody with some sensors. And the sensors, we place them in, sensor placing is an art, by the way, but over many years of work, we figured out the parts, and the field has figured out where to place them and so forth. But once you have them and the person moves, it moves in time. And so it'll have, so say that it's moving in that direction, it'll be outputting some trajectories, some motion trajectories. And they are then represented in 3 dimensions. So that's the curve I had there before. And depending on the sampling resolution, which for example could be 240 hertz, right? You start sampling. So the person moves and it takes several samples. And if you connect those dots, that builds a position trajectory. So say that this is X, X1, X2, X3, the 3 coordinates, right? Normally you call them X, Y, and Z. So let's say that this is a pointing behavior and you have a target here to point to, and you start out here. Right? And so what happens is every time that you take a step, so this is position, let's call it P0, P1, P2, and so forth, and Pn. Every time you take a step, this is and it happens in an interval of time and also in an interval of space, which we would call delta P, and that would be the difference between this point P at time t at this point P at time t plus 1. And so that's a representation that is time dependent. Now, if this curve here can be traversed in with many different temporal profiles. You could have the same exact representation, plotted in a different color like that, and not have have a completely different temporal profile. So in that case, your P at time t and P at time t plus 1 has a very different delta in between. And so there is 2 deltas when you do that. One is the delta in a space, and the other one is the delta in time. So when Theo was telling us what he did, he took, after a pipeline of different steps, it looked something like that. And he took those peaks of a normalized amplitude from 0 to 1, and he took the interval timings of those peaks. So he worked in this domain. Today he showed us something in this domain, but in the previous examples he was showing us something in the amplitude domain. So in the scripts that I sent you, that I uploaded, you have amplitude and you have timing. And so you have build record amplitude and build record timing. And the difference is that in one case, you work on this domain of the amplitude, and in the other case, you work on this domain of the timing. So here is how it would look if you were to subtract one from the other. Oh, by the way, Theo, what you did is great. And there is a command in MATLAB to take that derivative. It's diff, D-I-F-F.
Yeah.
It does the same as shifting and by 1. And
Okay.
Yeah. So, so here's your delta P from the difference between the 2 points, right? And so now we computed we're going to compute it in a space. So what is the magnitude of that step? And we can do that with a with a norm, in this case, the Euclidean norm. So if we were to call that component x1, x2, and x3, the component of P, and then the component of the delta. So this is P1 and P2 in time T1 and time T2. And so the component of P, you have x1, x2, and x3 at time T. So that's P1. And P2 is x1, x2, and x3 at time T plus 1. And so, so you take this magnitude here by obtaining the difference, so you can then take the delta, which comes from the difference between the two P's, and obtaining the norm of that. So the square of each one of the components, and then take the components square, and then take the square root of that. And so that would come from that computation. So I changed the screen here, but essentially then, so that's your delta P. So you would say x1 at time t minus x1 at time t plus 1 square plus and then you take the square root of that. And that gives you the norm. So at each point, at each one of these points, you take your norm and you plot it. And you take your norm and you plot it, and so on and so on. And it turns out that, and so as it grows, it reaches the peak, and then it starts declining, and then you stop. And so this is 0 speed. And the speed would be in some units per unit time, and that unit time depends on your sampling resolution, right? So in this case was 240 hertz. So that means 240 frames in 1 second. So sampling around 4 milliseconds or so because 1 second has 1,000 milliseconds, right? And so turns out this kind of representation is very common in pointing behavior. It's kind of stereotypical of pointing behavior. Of course, you have other things like that when you're learning and like that, and then you adjust. You could have like speed up and get your peak earlier and then decelerate and slow. But the point is that you start out at 0 speed and you end up at 0 speed. In both cases, you're at rest. You accelerate and you decelerate. And this peak is very informative, so we use it in our data, right? So if I were to do a new slide, let me see how I do a new slide. New slide, okay. Well, except I didn't want that type of slide. Let me see if I have a better slide. New slide. It's defaulting to anyway, so we don't want that type of slide, but it's okay. So back to our speed, what we can then construct from any kind of data is the speed profile. So you have a time series data with different values that you're sampling at a uniform time scale, and this could be anything. Like in Nipun's case, it was like key presses, right? It could be the times sustained at key presses, which I think that's more like what he did. It could be the magnitude of something like weights. Like say you're taking weights, measurements, and so forth. And so you can have your different magnitudes and always obtain the difference between the two. And that differentiation if you take the absolute value, or if you take some kind of a norm, with absolute value is a kind of a norm, but in one dimension, but a kind of a norm in higher dimensions, you get positive values, right? So in that case, then very likely you fit a skew distribution in physical phenomena that comes from bodily movements, because there are limits. And the limits, you know, that you always start at rest, at zero. You always end up at zero, and you can always reach a peak, but that peak is limited by your anatomical constraints, namely the length of your arm, the length of your legs, the weight, and so forth. So you know that maximally you're going to get a range of that value for a given person. So if you have an arm that is, I don't know, 130 centimeters long, you will have a limit in how much you can speed, which will depend on the mass of your arm and the length of your limbs and the joints, flexibility in your joints, and so forth. But you can't overcome that, or you'll damage your joints. So that sets a limit on the data that we're collecting. And so then you know that when you take a lot of this measurement, like a lot of them for a long time, those peaks will range necessarily between 0 and the limit for that person. So that sets a constraint in how how motion is interpreted and analyzed and so forth. So any questions about that? So that's how, this is a vector field, and it's tangent to the curve. That's tangent to the curve.
Hey Liz.
At the point, yes.
Sorry, Nipun said he got booted out of Zoom. Do you mind letting him back in?
Oh no, yeah, that's weird. I don't know why that happened. Okay, yeah, he's admit here. So any questions about that? So that's how we compute. We go from position data to speed data. And of course, you can take another derivative between these two, another differentiation, right? That would be the acceleration. So this would be order 1, and this would be order 2, right? And the acceleration is actually perpendicular to the tangent, to the curve at the point. And that's how we compute. We used to compute the curvature, and in the other lecture that we're so. Okay, I'm going to stop sharing. Any questions about that? Were you able to see the screen? Yeah, I've never done that, so I didn't know if it was going to work. Seems to work. How did you get out of the Nippon?
I don't know. I think my Zoom crashed. So.
Okay. So any questions about that? That's how you compute. So given the position trajectory, that's how you compute the speed. You differentiate the position points, and you take a norm, like the Euclidean norm. There are other norms. Euclidean assumes that your space is flat, meaning that the internal angles of a triangle, so a triangle adds up to 180 degrees, but in non-flat spaces, that's not the case. So you could have positive curvature or negative curvature depending on your problem domain. But for the time being and for the purposes of our class, we assume Euclidean flat space. And the Euclidean norm then allows us to compute the speed, and from the speed then we can compute the fluctuations over time. So so any questions so far?
I have a random question for like the acceleration. When we take the norm of it, do we consider the effect of gravity, or do we just ignore that?
So usually the softwares these days separate the gravity component.
Okay.
So it's two components, the motion component and the gravity component.
Okay.
And so now that acceleration from the accelerometers is different from this acceleration, in that in this acceleration, we're deriving it from the position data, but in the accelerometers is collected by these MEMS, miniaturized electromechanical sensors,
Yeah.
which consider motion in relation to gravity. Whereas this one is positional data, so it's more kinematics based.
One thing that here about
Different.
the gravity is that at least for like the good thing is that when you study network of bodies like a body network, because gravity is the same everywhere in the body, it just adds a bias, but doesn't change the relationships between the bodies. And so I think that it's not a big problem for most tasks.
Yeah.
For that reason.
So it turns out that there is a lab in Brandeis University. I mean, they've been around forever, since I was a graduate student, and they were really hot at the time. And they study all these phenomena in NASA in zero gravity environments, because, as you know, the astronauts, because of the zero gravity and the changes, their proprioception adapts when they spend a long time, and then they have to readapt when they enter again the Earth. And so they study people they are readapting, and also in the simulator of zero gravity. It's fascinating research, and you can see how it impacts motor control. And so how the brain actually compensates for all these things, and the lack of gravity. And so a lot of what we do it in the way we do it because of
the gravity.
Because of the gravity that we're subject to. But the moment that changes, our entire nervous system is going to have to rewire, and the brain is going to have to redefine a lot of what it does. We just take it for granted because obviously it's a steady thing, and it's like a fish in the water. It doesn't have to think about the water environment. The fluid dynamics that it uses are what was born in, and so on. But if we had to live in that environment, we'd have to readapt. So that brings me to the next lecture, which will include Ian Waterman. And Ian Waterman lost his proprioception due to a viral infection. And I invite you to watch his movie. And I put the link. So I placed that lecture in PowerPoint PDF in both Box and Canvas. I have yet to record. I was recording and had some difficulties. So, but I can basically just give the lecture, and we can discuss it in live. But first let's comment on if you have any questions on these kinematics parameters. And if you don't have any questions, then I'll quickly go through the part 2 of that lecture 1, which has the answers. So just show you a little bit of the trajectories. And then I set up the code for you to plot the trajectories and the different parameters that we can derive from the motions, from the motion data. So we could also go over that together. So did everyone see that? Did everyone see that motion data? in the box and in the canvas. Let me just, here it is.
I had a question regarding Box. Does
Yeah.
everyone has to download the folder? Because with other cloud services, you can set it up on your desktop and it automatically syncs up all the files. But Rutgers Box doesn't allow me to do that.
Actually, I had it. It did that automatically, filled out my hard drive. I'm still dealing with that. It's very slow
Okay.
now, the machine, slowed down the machine. So I don't recommend it
Okay.
because it doesn't discriminate. It just, unless, you know, like Dropbox, you can selectively sync, but I don't see
Yeah.
how to, does anybody know how to selectively sync in Box? Because I don't see anywhere where I could selectively sync. And so it's syncing everything. And like, if somebody dumps there like 30 gigabytes of data, which somebody did, your hard drive is full. And so that's happened. So now I'm dealing with that. I'm trying to get rid of and like trace where the data is that is filling up my, so I wouldn't recommend it. So let me, if nobody has a question about the kinematics data I just showed, then let me share with, I'm going to share the screen. Do you see it? The MATLAB?
Yeah.
Yeah, so I put this code in the box and essentially it takes this data from the dancers and I'm going to run it. So let me just close everything. I'm going to run the whole thing. It will create a whole bunch of figures. But essentially, it takes the trajectories that the phase space generates. And remember, the phase space is an active LED system, motion capture system. And it automatically segments those trajectories. And what it's doing here is also segmenting the, yeah, I meant to comment that out so that it didn't do so many, but these are segments of the overall complex trajectory. So I'll explain how that is done. If this doesn't bomb out on me because of the issues I'm having now with the memory due to Box. But it's computing in each of the segments is computing the curvature and the speed and the acceleration of the curve. And then is computing the deviation from a linear fit. So that's because locally with an epsilon step, you can linearize a highly curved trajectory. And so this I was trying to see the limits to that, the limiting values. So these are for the male and the other ones were for the female. So this goes through one curve and segments automatically all the little pauses. So as we move, we're not aware of it, but as we move, there are pauses in our movements. And from pause to pause, there is a segment that we can analyze the kinematics and the variability and so on. And so that's essentially what I'm doing here, deriving a waveform from the trajectory, inclusive of the, so that has everything. So this is the right hand of the male, trace that trajectory. It's very complex, as you can see. But from the Frenet frame, which is this little frame in 3 dimensions, so the red is the tangent vector, which I just described in the iPad, so that's just the velocity vector. Perpendicular to that is the acceleration vector, and then normal to the tangent, and then perpendicular to both of them, taking the cross product, is the green one, which is the binormal vector, and you can compute then using the Frenet frames formula, which you can find here. So if you go to Frenet, the tangent is the local derivative normalized, so that's the tangent to the curve, and then the normal is the tangent divided by the normalized. So you build from that, so that's the acceleration of the curve. The binormal is the cross product. Then the curvature is the, and the torsion. The curvature is the norm of that tangent, and so forth. So, so this is kind of how to build that and how to compute it in MATLAB. Where I was here, yeah. So very complex trajectory from just one routine, but if you put the Frenet Serret frame on, and that will move across the trajectory, and then you plot the speed profile, just like I did for each frame. In this case, is sampling at 480 hertz, and so it races, reaches a peak, and then declines, and so on and so forth, because it's very complicated trajectory here. These are the pauses that I was talking about. So every time there's going to change, the slope is going to change from negative to positive, you have a minimum. And when it changes from positive to negative, you have a maximum, local maximum. So if we go by the local minima, then we can see the pauses along the trajectory and segmented. And so what you were seeing there flying by are the little segments from pause to pause. So that's one segment, and so on. That's another segment, another, and so on. So you can do a lot of different computations. And this is the female curve, another complicated curve, because they're doing ballet. So this is not like a simple pointing behavior from a resting position to the target, or clicking behavior, clicking the mouse in a task. This is actual very complicated trajectories, and that would be the corresponding speed profile derived from the curve with the pauses to segment each one of these segments and then study their properties individually. So the torsion, the amount of curvature, and the amount of curvature and the relationship of the curvature and the speed in this case. And so there are very cool relationships between curvature and speed in motor control that follow certain, by certain law-like relationships. So this is the code. I encourage you to run it and like create this, just to play with it. Of course, when you finish with that, you end up having a, so I stopped sharing the screen, but let me share again so that we can go quickly from just to.
I had a question about pauses.
Yeah.
How are we determining pauses again? Is it just velocity, that detected velocity is 0?
I'm sorry, what? The pauses. So the pauses, so in some of them, the velocity actually is not 0. You see that there is motion there. So the pauses are defined by the changes in the slope from a negative to a positive slope.
I see. Okay.
So that's a pulse like that at the bottom. Whereas the maxima is from a change in positive to negative. So that's the maximum. And so these are critical points of the curve because it's a change in the slope. And that's why we use the peaks. That's the reason why we use the peaks to derive all these parameters. That's first order change. Of course, there's second order change. So then you can see the change of the change. And those give you inflection points that are important as well. But for the purposes of our investigations, we've been using the first order primarily because, and then of course the curvature is combining both orders and so forth. But a lot of the sensors, when we're looking for off-the-shelf technology, lower the sampling resolution. Although these days, you know, an Apple Watch at 100 hertz is pretty good. And so in the past, this was the problem because when you differentiate, if you have noise in the data, instrumentation noise from, say, you lost the data point and the software interpolated or something like that, and the interpolation wasn't necessarily a sample point real from the physiology. It was artificial. So when you differentiate, that's augmented, so it's exaggerated, so the noise is exaggerated. And so because of that, you're better off with first order terms for your parameters. But if your sampling resolution is high and you have good interpolation techniques and so forth, second order is also good. So but a lot of what we do is based on first order. So the speed of the curve. And the curve in this case is positional, derived from bodily motions, right? But you can think of it as a position in some space, so it doesn't have to be bodily motions, it could be any parameter space, right? So if you think of the gamma parameter space, that's also a trajectory in 2 dimensions when you sample many of these points, like Nipun, in the case that you have is one shot because it's just a static snapshot of the phenomenon. But suppose that these people are typing all day long, right? So that's a very long trajectory, and you can segment it using these techniques. And so compute the stochastic signatures of each segment, and then you trace that as a trajectory. And then from there, you derive first order terms again, and that's a speed in the stochastic space. So it's something that we were discussing today at lab meeting with G's data, right? And that's something that she's done already, because when you have very long data, you can afford to do that. And so this gamma parameter space is very handy because right now you're just plotting one point and then the scatter, and you'll have a snapshot of your phenomena. And that's just a static snapshot. It's like taking a picture, but you actually make a movie of it, right? And that will be a dynamic, a stochastic, and so you address the non-stationarity of the phenomena and so forth. And you can actually understand whether your phenomena is actually steady state, stationary or non-stationary, and how you can measure other things about it. So
no, that's fair, because one of the ideas I was thinking about was that if I want to detect in a paragraph which part is the lie, in that case segmenting becomes interesting, because the properties of the segment will differ from rest of the trajectory segments in the trajectory of typing. So that's where I think it would be interesting to see. So trajectory wise rather than. So
first you characterize the basic units of your phenomena, right? And you characterize, now you can know that if it lies in this particular place of the configuration space, of the space of your configurations of your phenomena, it likely has this particular meaning. Otherwise, it has this other particular meaning, but you have already empirically characterized that. And so when now you go from the picture taking to the movie, so to speak, you have a pretty good notion of when the points visit that part of the space, what it means, versus when it visits the other part of the space, and so on. It's going to be very dynamic, but you know, if it's landing and the convergence, the trend is in this particular part of the space, on average, that person is telling the truth.
Yeah. And with language, I think segments, there's an automatic a priori segmentation that gives into in terms of words and sentence boundaries. That could be interesting to look at.
Yeah, and also, like now if you go to you move to the realm of text, right? And now you have words with meaning and frequency in language. So you can weight each word accordingly and so forth. So then you can start studying the statistics of your language and so forth from this, using this framework, and it also makes sense. So anyway, so okay, any other comments or questions? No. I think, how about we take a break and come back? Okay. All right. Do you see this PowerPoint?
No, it's on your email. Oh, yeah. Now we do.
Okay, hold on a second. Because what's in the email? How about that?
That's
Huh?
we can see it.
But are you seeing like the
Here's
one
the
that?
presentation like setting. Like
Huh?
we can see the current slide and the next slide. It's like
Yeah,
a
that's not what I want. Hold on, let me see how I can share it. How I can share it that it actually does the proper.
If you go back to the screen, you can change it from presenter view to regular view. That's all it was. It was set up for presenter view, as though you were giving it in front of a classroom.
No, yeah, but the problem is that is defaulting to my screen one since I have two screens. Yeah. But let me see if I do screen two. And now can you see it?
Yes.
Yeah.
And the preview one, do you see it?
No, it's just
Good.
the
Okay, so yeah, I just had to set it to the default. Okay, so I'm gonna clip the lecture so that it starts from here. So this is the lecture number 2 of intelligent behavior analysis, and welcome to the class. And probably we won't finish it, so this will have to be like part 1 and part 2 again. And so this goes over the notion of agency and self-determination in autism and beyond, in other, in general. And it's chapter 3 of my book. And so I'll just go over some of those notions and some of the statistical analysis that we were actually mentioning. And I'm so glad that Theo brought the exponential distribution, because we'll go over that as well.
Is it really blurry for anyone else? I'm sorry.
Yeah, it is.
Yeah,
Blurry.
it is. Yeah, it is blurry. But I think that has something to do with Zoom. I don't think.
Yeah.
I feel like this is the same as the PDF you shared, so I guess we can open the PDF.
True, yeah.
You can follow through with the PDF.
Yeah, it's very blurry. I mean,
Very weird. So I don't know why that is.
it's not a connection thing, because it's uniform. It doesn't fluctuate. So, did you share screen, or perhaps you need to share the PowerPoint or the PDF? I think they're in PDF, right? The PDF and not the screen, because the screen resolution.
The PDF, yeah.
Yeah.
I have the PDF, which I also uploaded in your. Hold on a second. Let me find the PDF. And so in your box, I also put a Word file called Materials L2 for us for lecture 2. Do you know what it might be? That thing that box did just completely upset my computer. I'm dealing with it now. So I filled up the whole operating system hard drive, so nothing runs smoothly. Okay, so that's the PDF. And hopefully you can see, yeah. So let me see. So let me start again, share the screen. Can you see it? Can you see the lecture?
Yeah, but it's, well, no, I see a file, but it's still real blurry.
How about if you try sharing the PowerPoint only and not the full screen? Like the...
Yeah, no, that's what I'm doing.
Yeah, it's just the screen now still, so that's why it's blurry.
All right.
It also might have to do with your screen resolution between your two displays.
Yeah, but in the past, we're good. Let me see that. How about now?
Yeah, now it's good.
Okay, I'm just sharing the Adobe Acrobat screen.
Yeah, now it's much better. I mean, yeah.
Okay, so all right, so the first thing is like to define the level of discourse on agency that we're gonna be focusing on. So usually agency, if you Google it, like in Wikipedia, you see the terms for sociology, and it's kind of high level. So it talks about your agency in decision making and your ability to act independently and to make your own free choices and so forth. And then in contrast, they bring up this notion of adding structure in your life, which in our lives is sometimes obvious through laws and regulations, and sometimes not so obvious lately with privacy issues and, you know, Big Brother watching and that sort of stuff. And how we don't know what we don't know anymore, and other things that impact our decision making in social life, even without our knowledge. So we're making decisions constantly, and some of these decisions are actually being steered by an external agent without our knowledge. So that's an unfortunate thing, but it happens. Now, the level of discourse that we are talking about here is more physiological. It's more like the level of the functioning of the nervous system and the amount of volitional control that we can have over our actions, meaning that we intend to do something, our nervous system gets ready for it and does it, and it actually, in fact, confirms that it did what it actually intended to do. So the consequences of what you intended to do are match exactly what you intended to do, or to a first approximation, what you intended to do. But if you don't have that, and it's very common in autism, that's what we discovered, meaning that you intend to do something, but your body does something else and you have no control over it, then you lose your agency over your thoughts and actions, because then it becomes very dysregulated and disorganized. Your life becomes very difficult. So in essence, you want both to consider the brain and the body emotion when you're talking about agency, and not just one or the other, because they go together, they feed from each other. And you can see that in how the central nervous system and the peripheral nervous system are structured and how they share information. So I'm plotting here in a schematic form several maps that we have, well-defined maps that we have across the body, including in the facial, orofacial nerves and the nerves that innervate our bodies, and the different maps across. And we have two streams of information from the CNS to the PNS. That's the efferent information, and it's here marked with a red arrow. And we have the afferent information, which is backwards from the PNS to the CNS. And that afferent information, we also study it in reafferent form because there is a recursivity there that the brain generates these motions at the same time, self-monitors them and self-corrects them. And all of that information makes it back to the brain. So we're in this constant flow of motion generation, biorhythmic activity across all these levels. So you have the central nervous system, and in green here, I'm signaling a structure, and in red function. So usually this is like the neuroanatomy of the system and the neurophysiology of the system. Function is for neurophysiology, structure is for neuroanatomy. And so in terms of the central nervous system, you have the brain and the spinal cord as the structure that scaffolds our central functioning. And you have integrative and control centers that plan our actions and make sure they're executed and so forth. And the peripheral nervous system, which is quite complicated and rich, you have cranial nerves and spinal nerves, and those innervate the face and the body, again, in a schematic form showing here. And then in functional, you have communication lines between the central nervous system and the rest of the body. And it's a closed loop, so this information is constantly flowing. When you put a sensor, it's sort of like you're tapping into that flow of information. You're recording the efferent information of the motor system, innervating the muscles, but you're also, because of the continuity and recursivity of the signal, you're also making inference. So it's like a proxy of your reentrant afferent information. So you can then begin to disentangle that afferent information through inference and all this statistical analysis that we do. In terms of these peripheral systems, you have the sensory afferent, the motor efferent. You have motor nerve fibers that conduct impulses from the brain to the muscles in the body. And you have from the CNS to the end effectors like the hand and the feet, you have muscles and glands that are innervated, and the information in the red arrow flow in that direction. And so the motor efferent information is further subdivided into the somatic nervous system for somatic motor voluntary control, and that's particularly formed by skeletal muscles. And you have also the autonomic nervous system with visceral and involuntary functions, and that's scaffolded by cardiac muscles. So these are two different types of muscles that we have. And then you have they project into the sympathetic division, the parasympathetic division, and the enteric division. The enteric division is somewhat neglected in our field, but it's called the second brain, and it has a great deal of overlapping in terms of neurotransmitters and functions that connect through the vagal nerve, and so vagal tone is actually very important, connecting that to the brain. And it's an axis that is going to become very important in autism in the next few years. The sympathetic division is for flight or flight, and Mona is doing a lot of research here on applying these methods, and the parasympathetic division to conserve energy and for housekeeping during rest. So this balance is very important, and is appears to be disrupted in autism, according to research from our own lab and from other labs. In the sensory afferent systems, you have somatic and visceral sensory nerve fibers in terms of the neuroanatomy, and you have impulses from the receptors across the body back to the brain. So that's sort of the flow of information in a simplified schematic form. But often in cognitive science, for example, or in psychology, we're in this orange box here. From all this other stuff is not really looked at. So we're trying to open up that door because of the wearable sensor revolution and the impact that it's having in our ability to track continuously the motions of our bodies in different natural behaviors. So I'm not gonna play this whole movie, but I encourage you to go and watch it, but I do want to play just like the beginning and a little bit in the middle. Just so this is Ian Waterman here. It's an extraordinary case that we have studied, and that's what I was talking about, that they brought him to NASA to help study his motions. Can you see this? Can you see that?
Yeah.
Hello? Yeah.
We're seeing a link.
Yeah, it's black. It's black. It didn't start. Yeah.
Do you
We don't
see
see
the
a
movie?
video. No.
No,
The slide.
if you press the link, maybe from Dailymotion.
Okay, I'll try. I was playing because I'm in that link, and move this window away from the shared application. Hold on a second. Let me
put the link to the video.
let me stop
on the
sharing.
chat.
Let me stop sharing, and let me share again. I just maybe you can see it when I share again. So let me just. Do you see it?
Yes.
So I'm gonna stop there, but I encourage you to watch it. Let me stop sharing so that we look at each other's face. We've been working with Ian Waterman and Jonathan Cole, that's the neurologist with him since the late 90s, when they brought him to the States to study his case, because it's an extraordinary case. And as you heard, there are only a handful of people with this condition in the world, and he's the only one who has managed to actually walk, stand up against gravity, and have balance and walk and talk and type and just do everything that we do. But that requires a lot of effort. And we've measured that in EEG tasks. And we've also measured his movements, his patterns. And one of the things that was remarkable about his speed profiles and those peaks, how they distribute, is that they distribute exponentially, both when he intends to do something and when he actually interleaves motions that are intended with automatic motions. But in his case, though, there is no automaticity. He thinks about everything. It's not like us that we are automated at certain segments that are spontaneous, that they're happening. He thinks about absolutely everything. So his brain is really busy considering all of this and closing the loop with vision. And he also has a very acute auditory sense of auditory system, because we brought him to do an EEG study with him, where he had to, as it was a neurofeedback study, he had to control the cursor on the screen and learn how to control it mentally. And so thinking left or right, intentionally thinking to move the cursor, and he learned that task. But in the process, I had a soda in the room, and I took a drink, and it bothered him. He he could hear my swallowing, you know, like he didn't even know I was behind. I was standing behind him. I took a drink, and he just said, "Can you stop that? It's bothering me." Because he had to concentrate in order to move the cursor. And one of the things was the test was to learn to control the cursor visually, and then close your eyes. You know, we would then blind the person and call for the control auditorily. So they were not trained in the auditory domain. And the question that we had was whether learning intentionality to intentionally control a cursor mentally, visually would transfer in the degree to which this acquirability was abstract, in the sense that it could transfer to another sense. So we tested this in the auditory domain. So we blindfolded him, and when we blindfolded him, he had to take his hands and hold on to the table, because then he cannot close the loop. That opens the loop, and so there's no reafferent information, and so he falls. So he had to hold on to the table, and that required an extreme effort. And so my swallowing disrupted that attentional load. And so he asked me to not swallow while he was trying to do this. It's remarkable. And then we collected his data, and it did transfer automatically, like the other participants. Everybody transferred the ability to intentionally control the cursor mentally when they did it auditorily. And I have these movies in the presentation, so I'm going to try to share it in PowerPoint, because you can't see it in the PDF really. So let me try. But we studied Ian Waterman patterns. We've been studying since the late 90s, and we brought him back here in 2015, I think, 2015, because are you familiar with Oliver Sacks, the neurologist that writes a lot? He passed away recently, but it was his 80th anniversary, and Ian Waterman was one of his famous patients. And so they brought all his famous patients to New York City, and Jonathan called the neurologist